shows like we are not on. No, we are. It's fine on the recording. Well, thanks for coming, and we are focusing on the discussion sections for Sanibel proceedings. It looks like our meetings are look like survival race. Less and less people are surviving to the end of semester, but probably by the end of the semester, whoever will stay will get a perfectly polished papers to submit. Okay, one more survival. So I will briefly cover some ideas on what can be placed in the discussion section, and then we will edit discussion sections of those who submitted them, and in parallel we will listen to overview of discussion sections of even smaller fraction of attendees. So covering things that may need to be discussed. If you look to ancient times, to the Aristotle and Cicero, and ancient recommendations how to make public talks and writings, they recommended to have like 50% of discussion section. Right now we have maybe 10% of the whole manuscript, but we need to overcome the resistance of reviewers. Reviewers are instructed by editors to find any weakness. It's like a game. And we may anticipate which side of our papers reviewer may consider as a weakness, and refute, prepare an answer, fight back, even before reviewer does see it. So we can write, a reader may not believe that this is this way, but you have an argument that this approximation is justified. So basic idea is this. On other things, anything that doesn't fit into linear logic of narration going from figure to figure can be, but is still interesting, can be placed on into discussion. What else? All papers ideally are organized as proof of hypothesis, posed at the introduction and concluded as proved right or wrong in the conclusions. In the discussion, it is time to express personal opinion. Do I believe myself that the hypothesis was supported by the evidences from results? So if you have any unformatted thoughts which you believe are valuable and interesting, discussion section is right place for them. Any non-linear logic that is interesting goes into discussion. Any non-linear logic material that is boring goes to supplemental information. So the paper itself is fun to read. I plan to distribute this little forms as previous time. And I have forgotten the fourth thing, interpretation. So interpretation and comparison with experiment and other calculations. So if you are so inspired to do this research and all your free time you read literature about subject of your research, you may compare what you read and what you have found yourself with the literature and report this comparison in the discussion. Nothing of the listed above is necessary. Discussion is least formatted, least logical, most creative part. You can skip it completely, or you can put anything you like. So those are only suggestions. So you may, when your logic goes from results to conclusions, and you feel that some materials, some of your thoughts are important, you cannot give them up. But conclusions are too short, format of conclusions doesn't allow you to put it there, and results are too simple, you just jump from figure to figure explaining what you see. And in between you have some something what you can place through. And there are some ways to identify what you see, which processes can you identify based on what is computed. You may report some of the observations, because when you do calculations you try everything, and then you may identify what is most interesting and important. Thank you so much. And when you interact with your colleagues, you naturally tell most interesting things first. But if we are under pressure of logical organization of the paper, we can postpone or even skip most interesting things. Discussion is the place where we can mention it and not skip it. Right? If you make observation that, for example, bond breaking of a ligand, when ligand detach and you have like several orders of magnitude darker, optical properties of material, discussion is the right thing. And even if you do not completely understand why it is, if you understand it's good, if you don't, still right place to mention. Like, we did everything we can with what methodology allows, but this question still remains open. Such acceptance of incomplete thing are bad for conclusions, but are fine for discussion. Here are something that we already discussed about discussion. Justification, anything doesn't fit into result, and interpretation. So I'm going to distribute whoever submitted. We will sit and start editing, providing feedback, and as time allows, slowly, without rush on the background, there are 3 speakers who can share their an overview of their discussion sections. So it will be Fatima, Aaron, and Alisa, who probably will come a little later. I don't know how good and how helpful are these forms. Right now I think they are obsolete and one can redesign them better, but several years ago they helped a lot in this similar circumstances. So do not wait until presentation, just go over and whip. You don't want to see this, right? Do you have a pen to write this? Would you like to be the first to present?
I didn't know that.
Huh? Just go over your notes. Levi,
Yeah.
what do you see? Because
Questions, 58 Senate conference poster, Q1 through Q9.
okay, do you see the speaker? Like me right now? No?
No.
Okay, that's fine, that's fine. You don't, it's nothing interesting to watch. If you see the content, it's sufficient.
Okay.
So while we are editing, Fatima will briefly summarize main ideas of her discussion section. So I invite you to the stage.
First of all, I didn't know that I have to present this. It's okay. So I have encountered these questions in Sunnyvale conference poster session, in my poster session. So there are, I think, 17 questions. For the first question, I wrote, what we can learn from this research. So we learned ground state electronic structure, optical properties, and electron dynamics on silicon nanowires.
Good.
And question 2, so what is the benefit? This is Levi asked me this question. So which one is good? If electrons are faster or holes faster? So So at low energy transitions, it is good if the electrons are faster compared to relaxation.
So can you explain why for photovoltaic effect different rate is needed?
I don't know exactly the answer.
So you may focus on question number 2 again. Anyone see connection?
Doesn't it have to deal with that holes have a higher effective mass? So if the rate is slower than the electrons, then there's a buildup of charge which causes the photovoltaic to become less efficient?
Well, for photovoltaic effect, you need interface, and in this research, it is homogeneous nanowire. So as a standalone model, it will never give photovoltaic effect. It's some, even if there is a connection, it will be very indirect.
Like a catalyst?
For catalyst, yes, because when charge carrier is at the band edge, it is more active. And also, there could be connection to your main interest K point. So depending on the stage of relaxation, well, right now it is not yet in this calculation, but potentially if we go through relaxation, the majority of charge density for each carrier can move between different K points.
But it depends on the...
And yes, and material, depending on whether electron and hole share the same K point or different K points, system may become brighter or darker. Excitation is probably direct transition without change of K point. But during relaxation, depending on the different rates, electron and hole can relax to different areas, to different values of different K points, and then instantaneously the model stop immediately.
But in her model, the band structure is kind of more flat. So to change the K point, the momentum change will be very insignificant, right? Very small number in that case.
Mm-hmm.
So it's kind of...
No. If you do wave packet as function of K point, not in this distribution that is made here like with 3, but like with 100 K points. You can draw a distribution at which K point there is a higher probability to find an electron. And if this distribution is mismatched for electron and hole, then it will be predominantly dark electronic state. So it may change brightness, ability of model to emit light. But I can be wrong, it's my opinion. Okay, please go forward.
Yeah. And the third question is, what is the rank of Redfield tensor? It is 4-rank tensor.
Okay.
And there was a question, why there is no Redfield elements on off diagonal?
Okay.
So we know the transitions more likely occur between adjacent states from the Redfield tensor by Boston.
Question number 4.
And question number 5, why?
Wait. What is the connection to Fermi golden rule? So, I assume you know what Fermi golden rule is.
I know Fermi golden rule, but
Okay, so in Fermi golden rule there is a resonance condition that initial and final state should be in resonance. Then the transition will be most efficient. And if you go to adjacent states, they are very close in energy. If you go over the neighbor, several states away, they have much more different energy, and it slows down the elementary relaxation event substantially. So it is mismatch of resonance condition in Fermi golden rule. Okay.
and for silicon nanowire growth in 111 crystal direction, we can see at all k points except at k points 0.33, the electrons are faster. But for k point at 0.33, we can see the hole are faster. So there was a question why it is different than the other k points. So from the, if we see the density of states individually for each k points, we can see in density of states at k point 0.33, you can see there is a subgap on the conduction band. So it delays the dissipation of electron dissipation, so holes are faster.
Okay, subgap slows the relaxation. Good. Okay.
What is the application of this research? So in photovoltaic and optoelectric devices.
Who are most cited authors on silicon nanowires? Whom you should cite in answer of this question? Okay, I am writing an answer to you here. Ewan, do you have any memories? So there is a very strong experimental group in Berkeley with Pidon Young. I'll spell it here. And he has several science papers cited over 3,000 times. You can just download them and look. You answered correctly, but you need to add just citations or details. Like, also there are laser applications. One can make laser out of single nanowire. Okay.
Question number 7 is, how does silicon nanowire form along 001 direction? Is it cut along the plane only? Yes, if we cut the bulk silicon along 001. Oh.
It's interesting.
It's surface.
Everyone agrees or disagrees? I disagree. How silicon nanowires are formed?
One direction.
How they are fabricated? And it is, again, if you look for most cited papers, you will need it for introduction anyway. Any ideas among
Etching?
us? Huh?
Etching?
No. No. Let me see if it is a touch screen so that I will. Yes, I can probably draw right here. If you don't mind, I'll draw over. Do not leave. We will continue. I will try to do it on the side. No, it doesn't leave the trees. Okay. You see at least this.
Better choose pen. I guess that would be.
But pen doesn't leave. Okay. Good. So one makes substrate of either silicon dioxide or silicon. It's not as important. And then one prepares the gold nanoparticle. And on the top, one uses one of the compounds that Dr. Han may like. Silane gas. You know, methane, if you replace silicon, carbon with silicon, it will be silane gas. And its main property is that if it touches atmospheric oxygen, it self-ignites, by the way. So then one makes a chamber. It is not vacuum chamber, it is pressurized chamber, but it is isolated. And then one heats it up to a temperature of gold melting. Then the gold in the atmosphere of silane makes same as water makes to carbon dioxide. it dissolves it. In soda that we drink, there is a huge amount of dissolved carbon dioxide, right? Gas dissolved in liquid. Same way, silicon dissolves in gold. Actually, silicon dissolves in gold and hydrogen escapes, evaporates. This is actually surface science. You may like it. And then, instead of gold, it becomes the eutectic alloy of silicon X, gold, Y. And when this alloy touches at the area where it touches the solid surface, the question is the most interesting, intriguing thing is that silicon melting temperature is twice as big compared to gold. So gold melts at whatever, whoever's from experiment should know better, but like 500, 600 Celsius, and silicon is over 1,000. So silicon goes to the lower end of this cluster and deposits from liquid to solid, crystallizes. And then this metal cluster grows up as a mushroom. And it leaves the, let me draw it once again, mushroom, the leg and a cluster on the top. Gold cluster grows up and leaves a trace, leaves a silicon nanowire. So this is solid, this is vapor liquid solid technique, VLS deposition. So not etching when grows it. And the question which crystallographic direction pops up is really interesting, I don't know. But maybe by modifying the substrate surface, pressure and temperature, one can induce growth in different crystallographic directions. Okay, I didn't damage your question 7. You can still read it. Okay.
So question 8 is there any experimental study on this? No.
There should be. If you, we should look through literature. It's very probable that there are experimental studies. Again, we'll talk one-to-one about going through Web of Science.
I thought here, like, the question was actually like, did we do any experimental study? Research theory. Okay. And then question 8, in electrodynamics figure, x-axis represents what? So it's the time logarithm scale and it is fixed.
Okay.
So question number 10, what is the subgame? What does it mean by subgame? So there was sparse density of states in band edge.
Okay.
And question 8, what will happen in case of transition from one K point to another K point?
And your answer?
My answer is we assumed momentum is conserved in this research. We are planning to study further when momentum is not conserved.
So suppose that you have completed the next step. But what happens physically? We know that there is a momentum conservation law. So if electronic system goes from state with 1K value of momentum to another value of momentum, where does difference of this momentum go to? What happens? Anyone wants to help to Fatima? Javed should be most prepared to answer this question.
I didn't follow this. Which number question?
12? The lucky one.
11, actually.
Okay, 11? Yes, okay.
Yeah, it can be, it depends on the momentum change of these two points.
You didn't answer anything.
The question is can be travel or not? It's dependence on the band structure.
What happens to momentum?
If
How does it contradict to momentum conservation?
if momentum, it need to be conserved momentum, but its momentum change is less than kt, so it can be transferred from one k point to another k points.
So what Jabet is telling, he wants to violate momentum conservation, and he tells that it is an okay approximation. For writing code, you are absolutely right. This is the best way to write code.
No, I mean,
But
no,
there's
I
better answer.
if the momentum change is less than kt value, then can I do it?
You are right practically, but for absolute precision,
We need to conserve momentum. It can go
Yes.
to the one.
And Levi,
Yes.
do you have your version of answer to question 11?
12.
11.
We use it. My question is true.
I think they're both the same question.
Yeah, both the
Okay.
same. Let me reformulate it for Levi. Can I?
Yeah.
So, consider electronic relaxation from state with momentum value k1 to state with momentum value k2. Suppose that we have written a code and such transition occurs. Is it allowed? Does it follow momentum conservation? Or it violates it? Or there is a third opportunity and explanation? What happens to momentum when electron changes the value of momentum?
I would assume that it is able to do it. And
Okay.
I would assume that the system pays the price for changing its momentum, which would mean that the kinetic energy of the electron would either go up or go down depending on the relative kinetic energy of the two K points.
Okay.
But I could be completely wrong.
No. You are brave enough to recognize the problem. Did you play billiard?
Yes.
So, what happens if one ball collides with another one?
Depends on how you do it, but I believe the answer you're asking is if you hit one with the other, the ball that has the initial momentum will give all of its momentum to the second ball, and it will stop, and the second billiard ball will continue.
Excellent. So, your first ball is electron, mentioned in the questions in Fatima's work. What is a second ball?
I would assume that that would be a phonon
Yes,
or lattice
exactly,
vibration.
correct. Yes, you are absolutely right. So the momentum goes away with a phonon. Right now, we assume no momentum for phonons; they are just vibrations. But if you discuss things rigorously, each phonon has not only energy but also direction. In solids, sound waves can go in different directions. One can assign momentum. And yes,
Would you have to quantize this momentum? Because I know I was listening to a talk by Eric Hobby, and he was saying in his silicon, I think quantum dots, there is like quantized energy levels for the momentum, and due to that, one facet or one direction has much smaller quantization, so it can go through that way, where if you go through a different direction, it is hindered and you don't get PR.
quantizing momentum is good, but it is not necessary.
Okay.
There is a semi-classical approach when electrons are quantized and nuclei are classical. You just need to when you solve for your normal modes, you need to do it with solid state software that assigns not only energy but also momentum. Right now
Okay.
we do not have it, but in discussion one can mention it. So the answer is that excess of momentum will be taken away with a phonon. Make sense? Okay, please go forward.
And question number 12 is the same as question 11. So question 13 is this calculation time dependent? The answer is no, since there is no time dependent potential. So we used time independent Schrodinger equation, Korn-Sham equation.
Everyone agrees?
We do use those. We use those as like building blocks to put into other equations.
So the ab initio tools, the codes that we run, they are based on things that you've mentioned, on time-independent Korn-Sham equations. But in fact, the Redfield equation is time-dependent. So globally, we do solve time-dependent equations. And time-independent are just our auxiliary tools.
Question number 14. In Redfield tensor, why some elements amplitude so high? The maximal absolute values appear for those elements described in the section. The high transition probability, I would say.
Can I ask a clarification? What does question 14 mean?
Yeah, I think
What amplitude are you saying? What is amplitude?
Like there are some bars, right, on the Redfield tensor graph. So why those are, some of them are so high and there is
But what is that in bar indicates?
Redfield tensor element along z-axis.
So it's Fermi golden rule transition probability from one alternate state to another one. I think your question 14 is connected to question number 4, and answer is the same. So when resonance condition is matched because of delta function in Fermi golden rule, the transition probability grows like crazy. So it's resonance conditions.
Question number 15, why elements of Redfield tensor are higher on one side? Because the density of state is higher in that side.
Okay.
when you say one side, do you mean like conduction and valence band side?
If you look at the Redfield tensors, either valence band or conduction band, the elements are higher, right? At some k points in valence bands and some k points in conduction bands. So why? Question.
Ideally, it should be also non-symmetric across the main diagonal. On one side it should be higher, on another lower, because one is relaxation, another is thermal excitation. Okay.
So in a single word, what we can learn from this poster, it's kind of similar to question number 1.
Huh?
So in a single word, what we can learn from this poster? Answer is the photo-induced non-radiative electron dynamics.
Well, it's not a single word, but it's like today's question of Immun about German language. There people try to combine like 2, 3, 5 words in one. Okay. You need to add momentum resolved for the induced non-radiative electrodynamics in silicon nanowires.
And the last question is what we can learn from Redfield tensor. So Redfield tensor represents the transition.
You can learn the transition probability of population. Thank you. Correct. electron population. Yes, it's basically answer what is Redfield tensor. Is it the last question?
Yeah.
I have one more. If I haven't started reading your actual discussion, is there any correlation between what you presented here and what you written in your discussion section?
Not all of them.
Do you plan to transfer some material from this presentation in your discussion session?
Yeah, like I included some of them, but I think a couple of questions might go to result section.
Okay.
Not all of them in the discussion. And
Okay.
I'll try to include more.
Okay. But thank Fatima. Device, thank you for the loud applause.
Oh,
Across the states. I was just taking brief notes. I didn't read this. I will read and provide separately.
Yeah, it is yours.
That is John.
Yeah. Okay. While we are continuing to edit, an unknown author of this masterpiece is invited to continue the discussion.
This is my second slide. This is my first slide. This is the important stuff I wanted to talk about. So last week I was at MRS in Phoenix, which is shown on the map in Arizona here. And I have a cousin who lives in Flagstaff, and I get see her like once every 2 or 3 years, so I figured, well, it's been about 3 years, so I should probably see her. So I took the weekend, went up to Flagstaff and visited her for a while, and she is big into competitive biking, so she took me out around that area because it's very mountainous and it's known for its mountain biking. So here's Flagstaff. This is the town that she lives in. That's where I was this weekend, and this is like the two big mountains you see riding north. Is if you're taking 17, going up to Flagstaff, and we did do some mountain biking on there, and it was a little bit too much for me, and I left parts of my body on that mountain. Just like took a nice little dig, and yeah, I kind of look like a leper from these wounds. My knee's a little worse. It's getting better, but
So you will not forget this trip.
there'll be a scar. I think there's a little divot in my knee.
Did you do any trekking in Sedona?
Yeah. So this is where we trekked to. This is a submarine rock because, well, it's pretty aptly named. Kind of looks like a submarine. You kind of start out near the bottom. You kind of work your way up to the top, and then it's just like a really gorgeous view, like all the way around. So this is just So yeah, if you're ever in Arizona and you have time to stop through Sedona and Flagstaff, I would highly recommend it. Just because I love it.
How to interpret the upper left?
Oh, that's I forgot about the In-N-Out burger. So that's like a chain restaurant that's only.
So what does it mean, in and out?
So it's like
What is coming in? What is coming out?
us, fast food. You get in, get your food, get out.
Okay.
So it's fast service.
This are first.
So it is people coming in and out.
Yeah, but it's like McDonald's.
Not the
Well, it could be the food too. You never know. But yeah, they're kind of like, well, they're only like located in the Southwest, so it's like if you go into the Southwest, you have to eat them just because it's like you can't eat it anywhere else, and it's a tasty burger.
Okay.
So yeah, that's just a little, just like if you're ever in the area, stop at these places. So I guess on to business. So I was traveling pretty much all morning, so I didn't see Dimitri's email about the discussions until today. But I guess if I was thinking,
I didn't send it until today.
Or I mean today afternoon. I can't remember. I slept most of the day because I had to sleep at the airport last night, and like you don't really sleep at an airport if you have to stay there. So. So yeah, so instead of writing my discussions, I just put down a couple of bullet points for the sections of my paper that are kind of outlined. So I have ground state, electronic structure, molecular dynamics, non-radiative relaxation, and then the radiative relaxation, and just a couple of things that I should mention in the discussion just because they'll be important for describing the paper. So obviously for ground state electronic structure, like the low-hanging fruit is band gaps, because no matter what paper you write, you have to write about whether your band gap corresponds to the experiment and whether it does for the right or wrong reasons. So that's something usually reviewers will ask about. And then probably the biggest thing that I have to talk about in the ground state electronic structure is just the orbital ordering for the d orbitals in the doped quantum dot.
So what do you mean ordering?
So like
Ordering in respect to what?
like energy levels. So like
And-
the splitting of the d states.
So just they're ordering in respect to each other or in respect to intrinsic moment moment?
Both. Because just looking at the d orbital ordering itself will give an idea of whether it corresponds to the ligand field it's in, because those should match up. So that's kind of something that you should pay attention to. And then since we're looking at optical properties or transitions between d states, you want the d orbitals to line up correctly with the perovskite as well. Yeah, so looking at the energy levels of the d orbitals in two different ways. And then for the molecular dynamics, the two big things to look at for that section would probably be the PL blinking along the molecular dynamics trajectory and the ligand surface dynamics, which are, I don't know, they're kind of the same topic. So basically, in experiment, you usually see that the light emission at any instant in time is kind of random. It kind of switches on and off. And we see that with this system as well. Over like 50 steps, you see the oscillator strength go bright and then dark, bright and dark. So that's something that people would be interested in seeing. And then there's also some other things too you could look at, as like bond distances of the surface, and then like.
Is it true blinking or it is just similar effect?
You mean what we computed, or
Your oscillator strengths going on and off along molecular dynamics trajectory. What is the typical order of magnitude for experimental observed blinking? How long does it stay on and how long does it stay off?
I don't know. Because I guess I didn't really know about blinking until someone at MRS presented about it. So it's either
I'm very intrigued and in your discovery of this relation of rapid change of oscillator strengths along the trajectory, but it could be effect similar to blinking, but different from what experimental blinking is, because you're observing jumps in oscillator strengths on like 20 femtoseconds on, then 20 femtoseconds off. And on experiment, it is like nanosecond on and nanosecond off. So
yeah, I guess I didn't see the time scales that they had on there.
So it would be safer to see like analogy. Do not claim that it is ultimate computational description of blinking phenomenon.
Right. I just saw the trend showed up both
Okay.
experiments.
Okay. Yeah.
And then, so for the non-radiative relaxation for all the systems, biggest thing would be comparing this effect of spin orbit coupling compared to just spin restricted or spin polarized.
Previous section about dynamics and blinking. Just for refresher of memory, what are your observables to quantify ligand to surface dynamics? Because if you want to track each individual bond, you'll be very tired because there are like about 100 critically important bonds.
Right, it would be like an average, because you can do that in Excel. You could probably pick up closest neighbors.
Did you plan to do radial distribution? You don't need to recompute anything right now. It's just for future and for discussion.
I know we talked about it for another system, but I guess I didn't think about it for the surface ligands.
Who is doing in Dr. Killian's group? Who is doing core shell? Levi?
Mhm.
So when you have bond distance between for pair of atoms where one atom belongs to core and another to shell, how do you monitor average change of this bond length? Which numerical tools do you use?
So I haven't done it for any of the papers, but what I normally do is we know which atoms are in the core and which atoms are in the shell, so we can split them into two different like categories, and then you could do the radio distribution function.
Good.
What I did was FFT of the interatomic distances. Are you trying to figure out which atoms are bonded to each other?
Yeah,
Or,
I like your answer about radial distribution function. Do you
if
know
you
how to
really-
plot it?
Yeah.
Okay, good. Aaron, do you have experience to plot radial distribution functions?
I've done it once or twice. But
Okay,
not off the top
okay,
of my head.
good. Then you guys can consult if needed and go forward.
The other thing that I did was I just looked up in like tables the bond distances between various pairs, and I neglected anything that was like 125% above that, just so then you get the nearest neighbor effect.
Mm-hmm.
But radio distribution function picks up nearest neighbors because you should have a major peak and then it should die, and then you can get like smaller peaks as you get further and further away.
Okay, yeah, good idea. Thank you. Thank you, Levi. Sorry for
Do you
interrupting.
have a code to compute it, Aaron?
I think there's a script in the bin. I know I've seen
Okay.
RDF in our bin anyway. So then, non-radiative relaxation. Yeah, just the effect of comparing the spin orbit computed red field tensors to the spin restricted or spin polarized ones, because they do show different trends between both of them. And I guess one comparison you could use is that both the non-adiabatic couplings and oscillator strings both depend on spatial overlaps, so you can make an analogy between those to describe some of those trends or try to get some sort of insight. They're at least proportional to the square. There's some other constants in there, but if you hold them out constant, it's like you should be able to get some sort of insight. And then we can also look for non-radiative spin flip transitions, which would be important because we're looking for when we get to radiative relaxation, we're looking for a specific transition. So it would be nice to know what the spin magnitude of like the whole system is at specific times throughout the dynamics. And then for the radiative relaxation, when we try to generate our PL spectrum, the biggest thing there would be determining the role of electron correlation in these systems, because we basically neglect it. But we know for d orbitals that they're very localized and they're correlated, so you should rigorously use what's the word I'm looking for? Not GGA, but like a hybrid functional. So we would have to comment on that because that's something the reviewer is going to comment on for sure. And then also determining for the spin orbit radius of relaxation, which orbitals participate, because it's kind of like a black box unless you actually do like the PDOS analysis, because you can't look at orbitals. So knowing like what the orbital composition is for each state would give some insight into how this quantum dot is emitting. And then these are just some poster questions and comments that from Sanibel and the MRS meeting that I was at that some people asked. Some of them kind of overlap. So the two biggest ones I always kind of got was the dependence on the doping concentration, because different concentrations, you'll get a lot of different effects for your dopants. So in our system, it's a high doping concentration, but since it's like fairly isolated, it's a good physical model for describing like just a single dopant, because it's basically just a dopant in a ligand field and then surface. So it's a good model to describe low doping concentrations. And then I also get some questions on what would be the effect of placing a dopant in different places in the perovskite, which is, I guess you really have three options. You have like the pristine, so it's in a perfectly octahedral field. You could put it at the surface, which it would be in a different splitting field, and I'm not sure how likely that would be. Or else it could be like in a defect spot, which is something we're not really looking at. So, and then one question that I got is why, for our molecular dynamics PL emission, that the line widths that we compute are wider than the experimental PL. I think one reason is that when I did molecular dynamics, it's like a big system, so I just kind of start and restart, stop it, restart it, stop it, and restart it, and the temperature wasn't very stable. So I think the average temperature was more like 330, 340 instead of 300. So that's going to widen the PL a little bit. And then,
So
compared to room temperature experiments, anyway.
Yulun knows a list of speakers at ACS in Boston, and there is a lady from City University of New York with double family name that sounds Spanish. Fernanda Sela. She was speaking at USD. If I forget, if you do not find, you can ask you.
Okay.
So she published papers, not one, several papers, that temperature in experiment and temperature in ab initio molecular dynamics are not one-to-one correlation because of accumulation of errors from different purposes, different origins. And her conclusion was, I don't remember exact numbers, but if you want to model 300 room temperature, you need, for coincidence with experiment, you need to run 200 Kelvin modeling, or opposite. So, and this discussion, right now there is no time to do recalculation, but ideally the question will be formulated this in several steps. First, rerun dynamics at several values of temperature, compute MD photoluminescence at each of those, find which computational temperature corresponds to width observed in experiment, and then discuss why computational temperature deviates from observed temperature. It will be same scientific value, but some people feel very much upset if they see curves not coinciding, and here there is a way to achieve it. If you lower temperature in simulation, it will match.
Okay.
Maybe in next or next paper.
So then,
More.
I can't really think of any other questions I had.
So no one was asking you about Rashba? No one was grilling you about methods?
Not at MRS anyway. It was mostly experimental people who were interested in doping.
Okay, do you remember any from Sanibel?
No, I didn't really get a lot of tough questions at Sanibel.
Huh? You didn't?
I didn't really get.
Because questions that Fatima presented were really good. It means that you, how to say, provoked audience well. That's it. Okay. Then I have a question.
Okay.
Experimental. The photoluminescence of manganese doped quantum dot is associated with spin flip, according to your
The literature.
and your computations,
Mm-hmm.
most likely. So, which experimental technique could potentially monitor the dynamics of spin flip? Which equipment should we buy? How, like, even if it is expensive, or whom should we collaborate with?
Some sort of fancy femtosecond laser.
Fancy femtosecond is not enough. What else needs to be there?
Wasn't that all transient spectroscopy?
Well, transient, it means that you have non-polarized, or polarization is isotropic.
I guess I don't understand. Or I guess I'm not getting context. Your electronic state with different orientation of spin and transition that has changed of overall angular momentum. Which experimental observable would? Oh, magnetization?
Yes.
Yeah.
So femtosecond magnetization, but other experiments for femtosecond magnetization. Without experimental background, I can imagine just walking around your test tube with a compass, but it's not very quick, right? So how to arrange what will be the experiment? Which technique? At least in which direction should we dig?
I don't know, whatever Felix does.
Huh?
Whatever Felix does.
Who?
Felix, I can't remember his last name, Drescher?
Oh,
Guy at
Felix. Okay. And what? Okay. But any of us has an idea?
There are an experiment like polarization, something, I forget the name, yeah.
Yes. So for this types of exotic transitions, the polarization of light should change. Did you saw the materials modeling studio or just IMAX three-dimensional glasses?
Mm-hmm.
Polarizers?
Mm-hmm.
So it should be femtosecond with polarizers. On both pump and probe, there should be either parallel or crossed polarizers, and maybe linear, maybe circular. So it should be time-dependent circular dichroism, something like this. So it is the direction where we should look. So
I have one first paper on that they use that method, yeah.
so you may check.
I've read those papers, but they don't make any freaking sense to me.
This paper.
Just
this
cite
one
them.
is for
Do not
fine
read. Just
structure.
cite.
They do the for cadmium selenide finite structure calculation, yeah. They define speed. It's an experimental paper, it's all paper.
If your paper will be strong enough, they will come after yourself anyway. They will find it online and send you email asking for details of calculations, and they will tell you. Do not worry, we know how to measure it, just tell us more how your spin flips.
Okay.
But it's better to mention it in the discussion.
Mm-hmm. That makes sense.
If indeed spin flips, as these calculations show, it potentially can be detected with femtosecond circular decrease experiment. Questions to Aaron? If no, that's about him.
Aaron, you don't need to applaud yourself.
I felt like I had to. I felt like you did a good job. Oh, listen, you missed my promo. But if you're ever in Arizona, check out these two places.
Okay.
I was thinking to go Sedona, but I didn't get this.
You got to next time.
Was it cold at the mornings?
In Flagstaff, yeah, because it's like 7,000 feet. And Sedona's hotter because it's like 5,000. So it's.
I wish I stayed a couple of days more and then go there.
I was going there maybe 11 years ago, and it was in the summer, but the water in a cup outside of the tent was freezing during the night.
Where you was in Friday? Conference or there?
Say that again?
Where you was in last Friday? I was in conference last Friday. I attended, but I didn't know that you were there
Oh, you were at MRS? Oh, yeah.
for 2 days only. Yeah.
Oh. What sessions were you at?
Friday, Thursday, and Friday.
Or like what?
Oh, my session.
Mm-hmm.
I went there. That's the one. I forget like the name of the one. She did some single fission type for competition.
I hung out. There was like 2 prof Skype sessions that were going on like simultaneously. So
Yeah, I
hopping
went
back and forth.
I saw one Pascal session, but I oh my god, that's why it is.
So we have another speaker who wants to share the summary of the discussion session. So let's keep continuing grading and listening at the same time.
Okay, well, I pretty much had to redo a whole bunch of calculations just because we wanted to split my results up into 2 different papers. So I don't have like half my calculations right now, which is why this is really slacking. But it should be done in the next couple weeks, but I'm not submitting the same journal as you guys are, so I don't have a deadline or anything. Okay, so these are the questions that I got at Sanibel. There's one guy who is really adamant that the structure of my quantum dot was gonna affect the absorption of, or like the oscillator strength of it. He was pretty convinced that I needed to look at it, but I have no idea how to even look at at what the change in geometry would specifically do for that. I don't even really know what he was asking.
So can you repeat?
Okay, so I optimized all of my quantum dots after I put the ligands on there, right? And it, he was asking specifically if the change in geometry had anything to do with the change in the absorption spectra.
Yes.
Okay, but
Always.
but how do I do anything with that? How do I put it in a ball and in a paper?
Okay. So question number 1. Anyone wants to?
Oh, that's not question number 1. That was just what I wanted to start with. Sorry, I didn't go. I didn't go in
So
order.
question number 0.
Okay.
Anyone wants to?
You just do like a single point calculation of like a perfect geometry. Do
Okay.
oscillator strengths for those, and then compare it to your optimized one.
But the optimized one is going to be different because it has a ligand on it.
So you
Well,
have,
right, you just put a ligand on like the unoptimized one.
And
You
just do it-
like just 1 times or 0 time steps.
Okay.
how many ligands do you have? Do you have the whole surface?
The one that the paper that I'm doing right now is just 1 ligand on the surface,
Okay.
and so that's the one I want to focus on.
Let's ask Levi.
Yes.
What is your opinion?
So it depends on what he's really asking about. If he's asking about the how we cut it from bulk,
No, I know how
and
to
then-
talk about that.
no, but if he's saying he does not believe that our cadmium-33, selenium-33, or sulfide-33 is the actual representation, representative form of the quantum dot. That's a whole separate question.
I don't think that's what he was
If it's
asking.
just how the, huh?
I think it's
I
just
didn't
how
hear
the
you.
geometry. I don't think it has
But-
anything to do with him not believing that we cut it from bulk.
Levi, can I
Yeah.
try to serve as an interpreter between two of you?
Yes.
I'll try to interpret question and then you'll try to answer. So it sounds to me as more general question about structure to property relation. What are the basic principles? Why geometry of ligands affect intensity of absorption and transition energy in absorption? Some general trends before going into details.
So if we're looking at the ligands, you could assume that since we're at 0K, right, because we optimize it using DFT, means that we're at 0 Kelvin. Our oscillator strength should be the highest possible of any geometry around that local minima, correct?
Okay.
So if his question is trying to ask, we have a single structure, we want to relate it to experiment, then doing like some MD simulation would be sufficient. Is that not what he's asking?
I don't know. I was just kind of hoping that you guys would interpret what he was asking, because he kept asking me the same question and I didn't understand what it meant. I think
Okay, let me try. If anyone, so in crystal lattice, each of given material, each atom has specific coordination number of neighbors at certain angles, at certain distances. And in cadmium selenium there are 4. Like each cadmium has 4 selenium neighbors, and each selenium has 4 cadmium neighbors. In the environment with 4 neighbors, atom or whatever ion feels itself happy. If a neighbor is removed, atom becomes unhappy and may do nasty things on overall absorption and emission.
okay.
So on surface, there are undercoordinated atoms. Undercoordinated means missing the neighbors. But if you put ligand on the spot, it makes the originally undercoordinated atom happy again. It provides missed coordination. Therefore, generally, ligands improve optical properties. So it's one mechanism that probably visitor of your poster was looking for. Just general statement before going into details. Second mechanism, when you have something adsorbed, the adsorbate may exchange charge, not in sense of dynamics, but in sense of statically, like be donating or withdrawing group, and change overall oxidation of the surface atom. Maybe not oxidation like by integer number, by some delta charge. And there's also changing of oxidation, even partial, also affects the optical properties. So you may mention these 2 mechanisms and then tell that, and what happens in this specific system depends on results that I have computed. But probably the person was missing general statement.
Okay. So would that be something that I would put in a discussion, or
You can put it even in the introduction.
Okay.
It is in the introduction, it would be better, and everyone who does responsible reading and reads from the beginning to the end will be prepared.
Okay, that
And-
makes sense.
Okay.
Okay, I don't have any of my stuff with me, so it's hard to like figures and stuff. Like I've got nothing with me.
But we were looking on your work several times. We have general idea.
Okay. Well, so he was really confused on what the network meant, which I'm actually working on right now, because I didn't have any, so this is actually number one now, which means that there's like the thiol is halfway between thiol and thiolate. So I'm looking on the TDFT to see if that has any impact on the absorption spectra. So I'm working on that, but that was just a question that I got a lot. And it kind of goes along with number two as far as the network, if it restores any sort of strength of transition, since thiolate has a tendency to be dim, at least in propylamine.
So I have a private opinion that can be wrong.
Okay.
But I would just put general statements that I shared, like changing the coordination and changing the oxidation.
Mm-hmm.
And then for any modifications of geometry, I would analyze whether this specific ligand or protonated or deprotonated affects coordination and affects local charge on the surface ion. And then make hypothetical analysis. Because this protonated and deprotonated probably gives different exchanges, different amount of charge. Therefore, some and it can be source of change in the oscillator strengths. I'll make a report and you'll think if you
Okay.
like or dislike it.
All right. I think I understand what you're saying, but I'm not 100% sure. So, the big question that I got, which I wrote my abstract on, which is the one thing that I actually can write it on, is how is it possible to have a positive binding energy? People did not like that. They thought that my calculations were off. Svetlana had an idea of recalculating it with a different basis set. I haven't done it yet. But that was a possibility of something that I could do to like.
So how do you interpret positive binding energy irrelevant to your work?
It just wouldn't want to be on the surface.
So it means like explosive,
Yeah, it just
right?
doesn't want to be
It will
there. Yeah.
fly away.
Yeah. But there doesn't seem to be like a correlation between charge and it leaving the molecule, because a negative and a positive ligand had positive binding energies. So I didn't really understand why that was happening. But basically, I just have to look at it more. And if I can't figure it out, I'll just put in the paper. I have no idea what happened.
Mm-hmm.
And yeah, but at least I'll address it. So.
Okay. Do you have positive binding energy for the same system in VASP? Or you never tried to?
Never tried it. Yeah, I haven't touched it.
Because when you do calculations in VASP, there is less choice of hybrid functions, but there is no basis set related errors.
Yeah.
Because all basis functions are orthogonal.
Fair
I'll
enough.
make recording.
You know, I'm just thinking of how much work that would be. Because I'd have to redo all of the binding, no, all
Not
the
all,
total
only the
energies.
problematic ones.
But then,
Again,
but like if it was problematic, then wouldn't that suggest that all of my binding energies were wrong?
I have a question. Why are you thinking that is a problematic? Is it why you don't think that system is unstable?
I mean, okay, because the bond distance between the cadmium and the sulfide and also the SH bond, they didn't increase significantly enough to cause a 2 eV energy difference in binding energy. It only happened in a polar solvent, so I guess there's a probability that the solvent.
But why you
An
assume
effect?
that is going to be should be increased?
For what?
That binding energy. So you're expecting that this binding energy should be increased, but it didn't increase as you expected. Is that sense?
Okay, one more time.
I mean, you're expecting that binding energy should be increased to either sulfur or something you said.
Yeah, with the distance, so
Mhm.
it should be more positive if it gets further away. I mean, that was what I had thought. That would be a trend, but I guess maybe not, because you're
No,
just
if
looking
it's
at me.
if it's like infinitely far away, the binding energy would be 0.
Mm-hmm.
because then the systems aren't interacting.
Okay, but then why is there positive binding energy?
It might have some conformational change on the quantum dot that makes it unstable, which then when you optimize it, but isolated without the ligand on there, that conformational change might
Wait,
be...
stop. Conformational?
So, if you put a ligand on it, right, your quantum dot will change just, like...
Are you just talking
how
about
it's-
geometry?
Yeah.
Okay.
So the geometry will change, or the conformation will change, or morphology will change. And that morphology change could have a high impact on energy. However, the ligand still wants to be on the surface. So it might be a two competing process where you have the quantum dot is being destabilized due to the ligand interaction, but the ligand still wants to be on the surface. Does that make sense at all?
Quantum dot destabilized due to interaction with the ligands, you say?
Yeah, I haven't seen the, I haven't looked into the structure to see what changes compared to the optimized with the ligand and optimized without, but that might be one reason why with the ligand you have a higher energy than without. No?
Okay, wait, so the ligand on the surface would make the quantum dot unstable, but the quantum dot would still want the ligand on the surface?
It might be in like some local potential energy surface minima where to remove the ligand, there's a high energy barrier,
Okay.
but where it's located on the potential energy surface changes the quantum dots geometry, which then causes during the optimization of the isolated quantum dot without the ligand to go down a different wow that then, that's a little too close, Dimitri.
Okay, I do not see how. Please navigate me. I'm zooming out.
A little bit more, keep going. A little bit more, tiny bit more, a little bit. One more little play. And there, that's good.
Can you see the
So does
speaker,
that
or
make-
you see? Can you see the speaker, or you see only the screen?
I see both,
Excellent.
but now it's readable. Does that make sense, my answer,
Yeah.
Alyssa, or no?
Yeah, it makes sense. I don't know how do you even prove that?
So one way that you could possibly do is start start with the optimized structure and do optimization iteratively, where you extend the quantum dot ligand out with some step size, and then optimize those independently and see if there is a point where the ligand goes away compared to going towards.
So in Gaussian, never mind, I answered my own question. I got it. Okay, I can do that. That wouldn't be that hard.
Or alternatively, you could do a relaxed scan, where you scan over the bond distance between the cadmium and the sulfur and the ligand, where then you could start with the optimized geometry and make it bigger and bigger until such point that if there's a potential energy hill, it gets over it and then drops back down. But we can talk about this later. I'll email you.
Okay. Okay. And then there was somebody asking that it was actually a proton on the surface and not a hydrogen, and I looked at it, and the electronegativity was positive, so that's a proton instead of just a normal
So
hydrogen.
you checked it through ESP maps.
I checked it through NBO. I don't know. If
Okay,
it's the same
okay.
thing.
Good.
Okay. And then okay. So this is kind of a similar question. I don't really know how to even address whether or not the structure changes based on solvent, because like how do you measure something like that?
Optimal interatomic distance as function of solvent. Right? What is your comment?
So I don't think you were here, but for I think it was Aaron's talk, we were trying to talk about how to inspect the morphology or the structure of
Is that
his
the radial
system.
thing?
Yeah, so you could do a radial distribution function
Okay.
where you only look at the like quantum dot atoms, where then you could see like major peaks. And I think I either have a code or I can easily write one that could pull out the final geometry, make the radial distribution function, and then you could look at the bond distances.
So it would be an overall bond distance, though, like an average?
What?
Would it be like an average?
No, so what a radial distribution function is, it's sum of pairwise distances. Which a pairwise distance is, you say, take atom A and find the distance between atom A and B. That's a pairwise distance. Then
So-
A, C.
What part of that is not an average?
Levi, it is probably too much details for brief discussion. So,
Okay.
but during next week you may want to consult and learn
Yeah.
what radial distribution is.
Okay.
It is not very complicated concept, but it's not usual.
Okay. Alright, and that was pretty much it.
Okay, then let's applaud Alicia. So we do have, whatever, 20 minutes to complete our grades, or how to say, reading. If some of you plan to complete earlier and depart earlier, I don't know if I will have Steam to send reminder early enough, but next time let's read and provide feedback to each other on the methods section. So since not each of us develop new methods in these papers, it is fine to borrow some templates. And you are welcome to chat to each other, borrow. It doesn't undermine the originality of your paper, if you know what to borrow and what to put. So methodology section should provide sufficient details for reader to reproduce your results. Or at least it should sound this way. Some people hide know-how secrets, but it shouldn't sound like you're hiding everything. And it is very, very applicable and appropriate to show equations. Okay, let's sit and read and distribute it back to authors. let me attract a bit of attention. So the work by John Fogel, whose POT stands for polar-oxide titanium. You may skip it or not focus on it because it is kind of not primary material of your interest.
It is pretty long, yeah.
Yeah, and he didn't follow what I've asked you to do, to separate discussion from results. But at least Levi's will do that. So I wanted to say three, but now at least two persons in the audience, Alisa and Aaron, could benefit from reading it or could criticize professionally. So what John does in what he calls resulted in discussion, he is dealing with the same structure to property relations between ligands and optical properties of quantum dots. Even if he doesn't use the keyword quantum dots, it is the same physics, same chemistry, same trends. So putting different ligands and seeing how they affect mechanism, how they affect optical properties. And you may borrow some language or style of thinking what you're writing, or you may criticize it because it is kind of new area for you. You're doing perovskite and cadmium selenium, and John is doing titanium dioxide, but it is same idea. Organic inorganic interface. Inorganic quantum dot semiconductor with some ligands placed, ligands of different nature adsorbed to different spots on the surface. And they predominantly change absorption spectra most strongly. Okay, end of the comment.
Would it be okay if I were to do a results and discussion instead of separating them?
It's a matter of personal preference. I don't care. I prefer having them separate because it is easier to organize. Results on the factual material, what you observe, and discussion are your own thoughts. But there are no rules among editors and reviewers. It's just, it will be less organized, but it doesn't mean that it will be wrong.
Okay.
I can share personal experience why I like discussion sections. And you could be witness of this, of what I'm going to tell. When you submit a paper to the journal, it is being reviewed, and reviewer requests some changes and asks some questions. And then you try to answer them and then stick them into the manuscript. But sometimes you cannot find spot where your answer may fit. It doesn't go to conclusion, doesn't go to introduction, doesn't go to results. And if you have some unformatted just answers, you just dump everything into the discussion.
Nice.
sense about Trump. You have pleasure from seeing other people fail. I guess I missed most of the context of that tweet, but it just sounds like Trump.
Whose is the unraveling the quantum nature one? Is it yours? Can I keep it so I can look at it? It's really good. I just like it as a template. That would be great.
You're looking for John's work? Yeah. So I'm looking at the very last version. It tells that this building to metal church transfer occupied some method group. It could be oxidation. It could be well-defined chemical product. With your chemical experience, you can ask this question. So.